Good morning, my name is George Vlahavas and I'm here to present our work, DeCStor, a framework that uses a public blockchain to provide a way to share files in a private and secure way. Public cloud service providers have become popular during recent years. Through these services, users can store their data remotely and access them at any time and from anywhere. In most cases, in addition to providing an online storage space, they also provide the means for file sharing and collaboration. However, they introduce significant security and privacy risks. A potential breach in the security of the cloud service provider may allow an attacker access to private data. Privacy may be an even more important concern. It is widely known that most cloud service providers access user files stored on their premises with the intent to harvest information about the users. They can then use that information to direct the user to other paid services or simply target them with more effective advertisements of third-party products and services. While this may be an acceptable trade-off for a large number of individuals, it is certainly not acceptable by everyone. And especially for enterprises and government organizations, this access to potentially mission-critical data may not be acceptable at all. To counter these problems, private cloud solutions have been developed. In these, infrastructure is managed by the user, organization, or enterprise. And while this may address most of the privacy-related issues with public cloud services, the cost of supporting their infrastructure falls on the end user. What's more important, they are also more susceptible to security issues. This is due to the fact that a small organization or an individual may lack the resources for proper maintenance of the infrastructure and related software, leaving known security issues unpatched for large periods of time. In order to address these concerns, we argue for designing a framework which allows the users to privately and securely share files using public blockchain technologies. Since it is not cost-effective to store large amounts of data on a public blockchain, our proposed framework uses the Ethereum blockchain together with Swarm, which is a decentralized storage solution tightly connected with Ethereum. In addition to these, we're using established technologies such as public key infrastructure and the AES cipher in order to ensure the privacy and security of the data. Everything is orchestrated using an Ethereum smart contract that we have developed. Let's take a look at how it works. Before any file operations are performed, a private public key pair is issued for each user. When a user uploads a new file, a file key that corresponds to that specific file is generated. This file key is simply a 32-byte randomly generated number that is then encoded as a base 64 ASCII string. The file is then encrypted using the AES-256 cipher, using the file key as the encryption key. The encrypted file is then uploaded to Swarm, and a hash that corresponds to the file's location in Swarm is returned to the file owner. The smart contract stores the file Swarm hash along with the owner's address to the Ethereum blockchain. During a file access request by a user, an appropriate method in the smart contract is initiated. The information that is passed to this method includes the recipient's address in the Ethereum network, as well as the public key that is attached to that address. These will be used by the file owner to encrypt the file key before providing access to the file itself. The smart contract also notifies the owner for the file access request by means of emitting an appropriate message in the Ethereum event logging system. This can be typically read by a monitoring application so that the owner is aware of the access request. When a file owner responds to a file access request, they use the recipient's public key to encrypt the file key to a share key that is specific to the recipient. That way, only the recipient, using their own private key, is able to later decrypt the share key. Having the share key, they can then get back the file key and in turn decrypt the AES encrypted file to its unencrypted form. The smart contract is used to store the file Swarm hash, which is the address of the file in Swarm, the recipient's address, as well as the corresponding public key. In that way, the smart contract acts as a logging mechanism of all people that have been provided access to the file. When the recipient wants to download the encrypted file, they use their own private key to decrypt the share key, recreating the file key in the process. They can then download the AES-256 encrypted file using its hash from Swarm and decrypt it using the file key that they obtained. During a file download, no data is stored by the smart contract. Only data that has been previously shared between the file owner and recipient is used to download the file from Swarm and decrypt it using the file key. Since we are using a public blockchain, smart contract actions incur certain costs. The following calculations are based on cryptocurrency prices during May 2020, but prices have not fluctuated considerably since then. So, the first cost concerns the deployment of the smart contract on the Ethereum blockchain. This is a one-time cost and should not concern users that just use the smart contract to upload and share files, and should only concern the user that deploys the smart contract. Still, this amount is less than $10, which can be considered trivial for most. When users issue a transaction to the smart contract, either for uploading a file, requesting access to a file, or providing access to it, the cost is not proportional to the file size. This is due to the fact that data that is relayed to the smart contract for each one of the respective functions is always constant, no matter the size of the data. All heavy calculations, for example encryption and hash calculations, are performed in the front-end part of the decentralized application, and the results are passed to the blockchain. Still, the amount of data that is written on the blockchain during these actions is very small, and the cost is minimal. The actual file download does not call the smart contract and has no cost whatsoever. With such small operational costs, the most important costs are likely to be Swarm storage costs. However, Swarm is still in early access stage and it has not been deployed to the main network yet. There is no way to guess how much it will ultimately cost to store data on Swarm. This will be proportional to the uploaded file sizes, but judging from similar implementations such as IPFS, that is not expected to be significant. Certainly within the same order of magnitude as what commercial cloud vendors charge, and probably cheaper. For these reasons, storage costs are not included in our calculations. A proof of concept implementation that consists of the smart contract, Web3 JavaScript library, and an HTML5 frontend is available under the GNU public license at our code repository in GitLab. There are some considerations that we have to keep in mind while using our framework. First, a potential issue with architecture is that once a share key has been decrypted to the file key that is used to encrypt and decrypt the data, the file key, or indeed the entire decrypted file, may be shared between third parties without the original owner being aware of it. While a solution to this issue could involve the use of some access control technologies such as digital rights management, DRM, in order to restrict access, it is out of scope with respect to this work. Such technologies could be used on top of our proposed framework without significant or in fact any alterations to it. Access revocation is however something to consider. If a user that has received access to a file is now considered untrustworthy, or the file key has been otherwise compromised, access to the original file should be revoked. To that effect, our proof of concept implementation includes functionality to re-encrypt and re-upload data to Swarm. During this action, the originally uploaded file gets downloaded, a new file key is generated, the file is encrypted with this new file key, and it is uploaded as a new file to Swarm. If the original file's owner stops providing incentive to other Swarm nodes in order for them to keep hosting the contents of the original file, this will be in time garbage collected and entirely removed from Swarm. Nevertheless, a window of opportunity for potentially malicious users that want to freely share the file with other parties still exists. Additionally, if the malicious user has already downloaded the full data from Swarm, there is no way to stop them from sharing them using any other means. To conclude, as a result of our design, the characteristics of our proposal include reliability, as all data is redundantly stored in multiple locations, confidentiality, since nobody other than the user that the file belongs to may learn any information about their data, integrity, since no unauthorized modification of data may take place, availability, since data should be available from anywhere with internet access at all times, cost effectiveness, since the associated costs are not prohibitive, and private data sharing, as users may share their data with other users that they choose to, and those users only. The added value provided by our proposal includes the combination of these underlying technologies in a novel way, coupled with an encryption scheme that allows for private data sharing that is isolated for individual users. Thank you very much for your attention. If there are any questions, I would be glad to answer them now.